Welcome back to ECE 320A. We're in Unit 9, which is our transfer function unit, and we're having fun. We're shaking systems. We're exciting systems with sinusoidal steady state. We're exciting systems with sinusoids, and we're looking for the sinusoidal steady state behavior. That's a part of homework number 9, and exam number 4 will obviously be made up of material from this unit. And exam number 4 will happen at the end of Unit 10. And Unit 10, just as a foreshadowing, is working with Bode plots, or the frequency response behavior. So we'll be able to sketch these plots and immediately extract from those magnitude and angle that we need to determine these sinusoidal steady state outputs. In this video, what we want to do is work through an example that now, boy, the work has been done. Now all we have is a transfer function. Find the sinusoidal steady state output of a system when we excite it with a sinusoid, and we already have the transfer function of that particular system. Let's suppose now that we have this transfer function, capital H, and what's the order of our system? How many effectively energy storage devices do we have if this came from an electrical circuit? Our system has a denominator polynomial that is order 2. It's a second order system. Is this system strictly proper? Remember what strictly proper is? Strictly proper is asking the question, is the numerator polynomial strictly less in degree than the denominator polynomial? And in fact it is. We have a first order numerator, we have a second order denominator. This is a strictly proper transfer function. We have a real pole at 5,000, and we have a quadratic denominator, and we could factor that denominator and determine where exactly it is, but maybe we don't even need to know. What we do need to know is what? As long as this particular system has a denominator that's monic, do we remember what monic is? Monic is when we've normalized the leading coefficient in our denominator polynomial to have a value of 1. So whatever that was, it's now been absorbed into the numerator's coefficient of 1,000. So if that was actually a 2 before, we've now factored that 2 out, and that makes our linear coefficient 6,000. It makes our constant coefficient 25 times 10 to the 6th, and it's now divided into, let's say, 2,000 upstairs to produce 2,000 divided by 2, or 1,000 for our net magnitude. And this particular transfer function is in what form? The form now will be important when we get into chapter 10, or I'm sorry, unit 10, but it's also important here because we will eventually be talking about poles and zeros, but in this case we do have it in a pole zero form. That's now our pole zero form. We haven't explicitly found the poles, but we can say something about this particular system. We can say that those poles are actually located in the complex, in the left half of the complex S-plane, because one, it's monic. Once that we've normalized the denominator to be monic and it's a quadratic, then all we need to do to determine whether or not those poles are in the left half plane is to check, is this coefficient present? Is it there? And yes, it is. It's 6,000. And is it positive? And yes, it is. There's a positive number there. So the linear fact coefficient is present and positive. The constant coefficient is present. It's 25 times 10 to the 6th, and it also is positive. So h of s, its denominator, has all of its roots in the left half plane. So h of s is stable. And the reason that it's stable is because the coefficients of the denominator exist, they are present, and they are positive. And that's only can be used when we're dealing with a second order. We can't apply that nice little trick or strategy to anything higher than a second order. This is only true when we have a second order polynomial and that particular polynomial has been normalized to have a leading coefficient of 1. A second order monic polynomial allows us now to check, are those coefficients present and positive? So now you can jump up and down, you're present and you're positive. Yay, you're positive. So now you have present and positive for these coefficients. You know you have a stable h of s. That allows you to use our formula for computing the sinusoidal steady state output based on just knowing the input, its frequency, its amplitude, and its angle, and the transfer function h of s. What's the frequency that we're concerned with? What's the excitation frequency? How are we shaking the system? The frequency of the input waveform is now the key frequency, and in this particular case, that's now 5,000. Omega naught is 5,000 radians per second. That's our important frequency, and once we have that, now we can continue. Now we simply evaluate our transfer function on the imaginary axis at that omega naught location. So we're on the imaginary axis, that's the J, and we're up at a location 5,000. So we've walked up the imaginary axis to a location of 5,000. That means everywhere we had an S in our transfer function H, we replace that S with J 5,000. We had a scaling factor of 1,000. We had S. So there's J 5,000 plus 5,000. That's going to be somewhat straightforward to compute. Then we had S squared. So we have J 5,000 squared. And we know what J squared is. That's minus 1. Plus 6,000 S. So there's 6,000 times J 5,000 plus 25 times 10 to the 6. Or we now have 1,000 and 1,000. Let's say that we have 5,000 plus J 5,000. Let's factor out the 1,000 there. So we now have 5 plus J 5, which we have 5 real part, 5 imaginary part. We have really 5 times the square root of 2. That's the hypotenuse. Times 10 to the, we have 3 in the 5,000s, but we had 1,000 also. So that's 10 to the 6th. And the angle of 5 plus J5, that was over 5 and up 5. So our angle, maybe I should do it a different way. We were over 5 and up 5. So now our angle is 45 degrees. And this dashed line is now, this was 5 and that was 5. This is now 5 at a square root of 2. This angle is 45 degrees since we had equal real part and equal imaginary part. That's the numerator. The denominator, if we play all of the numbers together, we have minus 5,000 squared. And that basically goes away with the 25 times 10 to the 6th on the right-hand side. And we now have 6,000 times J 5,000, or we have 30 times 10 to the 6th at an angle of J, which is now 90 degrees. So that these 10 to the 6th conveniently cancel, and we now have 5 square root of 2 over 30, or we now have that 5 and 30 can be simplified, and we now have the square root of 2 over 6, or 1.414 divided by 6, at an angle of 45 minus 90, or a net angle of minus 45. That's now h of j 5000. And that we can now use. That's written in polar form. We have a magnitude and an angle. We now know that our sinusoidal steady state output is what we started with for x, which was a gain of 120 or an amplitude of 120. We scale that by the square root of 2 over 6. We have a cosine. We haven't changed the frequency of oscillation. We excited it at 5,000 radians per second. The system will continue to shake at 5,000 radians per second. We had an initial phase of 30 degrees in I, and we now need to adjust that by the phase of our H, our system transfer function, so that now Y steady state of t, or our output sinusoidal steady state, is now 120 divided by 6, or 20, times the square root of 2, cosine 5000 t minus 15 degrees. That's now our sinusoidal steady state output based on exciting the system with a gain of 120, or an amplitude of 120, a frequency of omega 5000 radians per second, an off shift of 30 degrees. Now we're delayed from that, and we now have a scaled or reduced amplitude. We now have 20 times 1.414 cosine 5000 t minus 15 degrees. That's now the sinusoidal steady state output given a transfer function and a sinusoidal input. That's how clean this can be.